Between the stars you can see, there are clouds you mostly can't. Vast, slow-drifting clouds of gas and dust, some large enough to swallow 1,000 solar systems whole. We call them nebulas. Some of them are nurseries, quietly building new stars out of almost nothing. Some of them are graveyards, all that's left after a star has already lived its entire life and died. A few are both at the very same time, in different corners of the very same cloud. Tonight, we're going to drift through 36 of them. The birth, the death, and the strange, colorful clouds in between. You don't need to hold on to any of it. Just let each cloud drift past slowly, the way starlight does. Let's start with the simplest question of all. What is a nebula, actually? The clouds that aren't really clouds at all. A nebula is, at its simplest, a vast cloud of gas and dust drifting in space, mostly hydrogen, the most common element in the universe, along with helium and small traces of heavier elements, all spread so thinly that most nebulas are, by Earth standards, nearly a vacuum. What makes them visible at all, often from enormous distances, is their scale. A nebula can stretch across dozens or even hundreds of light years, so even gas this thin, spread across a volume that large, adds up to something bright enough to see, and in some cases bright enough to be visible to the naked eye from Earth on a clear night. The word itself comes from the Latin word for cloud or mist, and for centuries, before telescopes were powerful enough to tell them apart, astronomers used it loosely for almost any fuzzy, non-star-like smudge of light in the sky, including, mistakenly for a long time, entire distant galaxies, which we now know are something else entirely. Modern astronomy has since sorted nebulas into several distinct types based on how they're lit, what they're made of, and, most interestingly, whether they're the beginning of a star's life or the end of one. Thin as smoke, spread wider than 1,000 solar systems, and depending entirely on which kind you're looking at, either a beginning or an ending. We'll spend tonight learning to tell the difference. Some nebulas are pure beginnings. The closest large one to Earth is happening right now, close enough to see without a telescope at all. The nursery you can see with your bare eyes. Look toward the constellation Orion on a clear night, and just below the 3 stars of Orion's belt, you can make out a faint, fuzzy smudge. Not a star, but an entire star-forming nebula, roughly 1,344 light-years away, close enough to be visible without any equipment at all. The Orion Nebula is one of the closest and best studied stellar nurseries in the sky, spanning roughly 24 light-years across and containing an estimated several thousand stars in various stages of formation, some already burning brightly, others still gathering mass from the surrounding gas and dust. At its heart sits a small, tight cluster of extremely young, hot stars called the trapezium, whose intense ultraviolet radiation is what actually makes the surrounding nebula glow, energizing the hydrogen gas around them and causing it to emit the soft reddish light that gives the whole nebula its distinctive color in long exposure photographs. Because it's so close and so bright, the Orion Nebula has become one of the most photographed and thoroughly studied objects in the night sky, offering astronomers an unusually clear, detailed window into exactly how stars, and quite possibly planetary systems very much like our own, actually come together. A faint smudge, visible to your own eyes on a clear night, and inside it, right now, thousands of stars are quietly, slowly being born. Orion shows a nursery already glowing. To understand how it actually happens, we need to look at the very first moment a star begins to form at all. How a star actually comes together from nothing. Deep within a large molecular cloud, gravity slowly pulls together a denser knot of gas and dust, often triggered by a nearby disturbance, like the shock wave from a distant supernova, or the slow gravitational pull of the cloud's own uneven density. As this knot, called a protostar, continues gathering mass, it slowly contracts under its own gravity, and that contraction generates heat, the same basic principle as compressing any gas, causing it to warm. Over tens of thousands of years, the core temperature climbs higher and higher, the protostar glowing faintly in infrared light long before it's hot enough to be a true star at all. If the protostar gathers enough mass, roughly 8% of our own sun's mass is generally considered the minimum threshold. Its core eventually becomes hot and dense enough, several million degrees, to ignite nuclear fusion, converting hydrogen into helium and releasing enormous amounts of energy in the process. At that moment, a star is truly born and begins the long, stable hydrogen-burning phase that will define most of its life. Not every collapsing knot succeeds. Objects that never quite reach that fusion threshold become brown dwarfs instead, sometimes called failed stars, too massive to be ordinary planets, but never quite massive enough to ignite and shine on their own. A star's entire existence is decided in that single threshold moment. Enough mass and a new light joins the sky forever. Just short of it, and something sits forever in the dark, almost a star, but never quite. That's the theory. One image, more than any other, made it real for the entire world at once. The photograph that made a nebula famous. In 1995, the Hubble Space Telescope captured an image that would become one of the most recognized astronomical photographs ever taken. 3 towering columns of gas and dust rising from the Eagle Nebula, roughly 6,500 light-years away, quickly nicknamed the Pillars of Creation. Each pillar is genuinely enormous. The tallest stretches roughly 4 light-years from base to tip, taller than the distance between our own sun and its nearest stellar neighbor. Within the dense gas of these pillars, new stars are actively forming, their gravity slowly compressing pockets of material until fusion ignites deep inside. The pillars themselves are made of cool molecular hydrogen and dust, dense enough to resist, at least for now, the intense radiation streaming from a cluster of hot young stars nearby. That same radiation is slowly eroding the pillars from the outside in, a process we'll look at more closely in just a moment. In 2014, And again with the James Webb Space Telescope in 2022, astronomers recaptured the pillars of creation in far greater detail, including infrared views that peer straight through the dust to reveal the young stars actively forming within the same ancient cosmic nursery, photographed generations of telescopes apart, still quietly at work. 3 towers of dust and gas, 4 light years tall, doing the same patient work they were already doing long before any human eye or any telescope was ever around to notice them. Those towers look permanent. They aren't, and the same light that makes them famous is also the reason they won't last. The same light building new stars is slowly destroying the pillars. The pillars of creation aren't a permanent structure. They're being actively eroded right now by a process astronomers call photoevaporation, intense ultraviolet radiation from the same young massive stars whose light makes the nebula visible is also slowly stripping the pillars away, layer by layer. This radiation heats and ionizes the outer layers of gas, causing them to stream away from the pillars entirely, gradually shrinking them from the outside in, a bit like sunlight slowly evaporating a block of ice, if that block of ice happened to be several light years tall. Based on the erosion rate astronomers have measured, some estimates suggest the pillars may have only a few 100,000 to a few million years left before this process, along with the shockwave from a supernova astronomers believe already happened nearby, breaks them apart entirely. A genuinely long time by human standards, but a fairly brief chapter in the multi-billion-year life of a galaxy. Because light from the pillars takes about 6,500 years to reach Earth, some astronomers believe that a supernova shockwave may have already destroyed part of the structure we're currently observing, meaning the iconic image captured in 1995 might already be, in a very real sense, a photograph of something that no longer exists in quite the same shape out there right now. The very light that built new stars inside these towers is the same light slowly taking the towers apart. Creation and unmaking happening in the very same breath over a time scale too long for anyone to actually watch it happen. The Eagle Nebula's pillars are famous. A newer telescope recently gave us an even sharper look at a very similar scene in a nebula most people have never heard of. The cliffs that aren't made of stone at all. In July 2022, one of the first images released from the newly operational James Webb Space Telescope showed something that looked at first glance like a mountain range at dusk, golden, textured cliffs rising against a starry sky. It wasn't stone. It was the edge of the Carina Nebula, roughly 7,600 light-years away. Quickly nicknamed the Cosmic Cliffs, this image showed the edge of a young star-forming region within the Carina Nebula in unprecedented infrared detail. Webb's infrared instruments are specifically designed to see through the obscuring dust that would completely block a visible light telescope's view of the same region. The glowing cliff face is actually the edge of a vast cavity being carved into the nebula by intense radiation and stellar winds from nearby massive young stars, similar in principle to the photoevaporation eating away at the pillars of creation, just captured here in extraordinary new detail. Individual young stars, some previously entirely hidden by dust, suddenly visible as bright points scattered across the image. Carina itself is one of the largest and brightest nebulas in the sky, home to some of the most massive and luminous stars known, including Eta Carinae, a highly unstable star system many times more massive than our Sun, considered a strong candidate to end its life in a dramatic supernova at some point, astronomically speaking, relatively soon. Mountains made of gas and starlight, photographed clearly for the first time only because a telescope finally learned to see in a kind of light our own eyes were never built to notice at all. Carina glows from its own young star's radiation. Not every nebula makes its own light. Some only borrow it. The glow that comes from the gas itself. Nebulas produce their glow in different ways, and astronomers sort them accordingly. The first type, called an emission nebula, genuinely produces its own light, not by burning, but through a process called ionization. Intense ultraviolet radiation from nearby hot young stars strips electrons away from hydrogen atoms in the surrounding gas. When those electrons are eventually recaptured by the atoms, they release energy in the form of light, predominantly a specific deep red wavelength associated with hydrogen, which is why so many emission nebulae, including the Orion Nebula from earlier tonight, appear reddish in long exposure photographs. This is genuinely the same basic physical principle behind a neon sign, energized gas releasing light at very specific wavelengths, just happening at a scale measured in light years instead of inches, powered by entire stars instead of an electrical current. Because this glow depends entirely on nearby hot stars supplying the energy, emission nebulae are almost always found in active star-forming regions. The presence of the glow itself is, in a very real sense, direct evidence that new stars are being born somewhere close by. A cloud of gas, quietly glowing its own true color across light years of space, not reflected, not borrowed, but genuinely, chemically, its very own light. The nebula that only shines with someone else's light. The second major type, called a reflection nebula, doesn't produce any light of its own at all. Instead, its dust particles simply scatter and reflect the light of nearby stars, the same basic principle that makes our own sky blue during the day, just happening around a star instead of a planet's atmosphere. Because this scattering process affects blue light more strongly than red light, reflection nebulas typically appear with a distinct bluish tint in photographs, a useful visual clue that helps astronomers tell them apart from the reddish emission nebulas nearby. One of the most famous examples surrounds the Pleiades star cluster, visible to the naked eye in the constellation Taurus. Long exposure photographs reveal faint, wispy blue clouds draped around the cluster's bright young stars. Dust the stars happen to be passing through, illuminated by starlight rather than being their actual birthplace. For a long time, astronomers actually assumed this dust was leftover material from the Pleiades' own formation, similar to the pillars and cliffs we've already looked at tonight. More recent research suggests it's more likely an unrelated cloud of interstellar dust that the cluster happens to be passing through right now in an entirely separate, coincidental encounter. A cloud with no light of its own, borrowing every bit of its glow from stars that were only ever passing through. Sometimes even the universe's brightest moments turn out to be a kind of quiet, generous reflection. Emission nebulas glow. Reflection nebulas borrow light. One more kind does neither. It simply blocks the light behind it completely. The cloud dark enough to blot out the stars behind it. Not every nebula is bright. Dark nebulas are dense enough clouds of gas and dust that they block visible light entirely, appearing as stark black silhouettes against the brighter stars and glowing gas behind them, rather than glowing or reflecting any light of their own. These clouds are made of the same basic material as emission and reflection nebulas, but are simply denser and colder, without nearby hot stars to ionize the gas or provide enough scattered light to see by. Paradoxically, dark nebulas are often the coldest, most fertile environments for future star formation, dense enough for gravity to eventually take hold and begin the whole process we looked at earlier tonight in near total darkness, invisible until stars eventually ignite from within. The astronomer William Herschel, observing one such patch of apparent emptiness in the 1780s, initially assumed it was a genuine gap or hole in the universe's fabric of stars, a real void rather than an obscuring cloud. It would be well over a century before astronomers correctly understood that these dark patches were actually dense foreground clouds, blocking the light of countless stars behind them rather than representing space at all. Some dark nebulas are large enough and dense enough to be easily visible to the naked eye against the brighter background of the Milky Way, a genuine patch of the sky that looks quite convincingly like a hole cut directly out of the stars. Not space at all, just a cloud dark enough and patient enough to be quietly building the next generation of stars in complete secrecy, entirely out of sight. Dark nebulas can be shapeless. One, though, became famous for looking exactly like something else entirely. The dark shape that looks exactly like a horse. In the constellation Orion, not far from the nebula we visited earlier tonight, a dense, dark nebula rises against a glowing red backdrop in a shape so distinctive that it's become one of the most recognizable objects in all of astrophotography, the Horsehead Nebula. First photographed in 1888, the Horsehead is a dense pillar of cold gas and dust, roughly 1,500 light-years away, silhouetted against the brighter emission nebula IC 434 behind it. The same basic dark nebula in front of bright background principle from the previous chapter, just arranged entirely by chance into a shape the human eye immediately recognizes. Like the pillars of creation, the Horsehead is being gradually eroded by radiation from nearby stars, and astronomers estimate it may fully dissipate over the next several million years, a genuinely temporary shape in cosmic terms, that simply happens to have formed during the narrow window of time when humans developed telescopes powerful enough to notice it. Modern infrared images, including recent observations from the James Webb Space Telescope, have revealed fine wave-like structures rippling along the nebula's edge, caused by the same radiation and stellar wind erosion process, texture invisible in the original 1888 photograph, only becoming clear well over a century later. A shape that means nothing to the universe itself, meaning something instantly and unmistakably to us. A horse's silhouette, built from cold gas, existing for a few million years purely by coincidence, right when someone happened to be looking. Every nebula so far has been about beginnings. Now we turn to endings, and the first one has, confusingly, nothing to do with planets at all. The nebula named for the wrong thing entirely. In the late 1700s, astronomer William Herschel, the same astronomer from a few chapters ago, observed a class of nebulas that, through a small telescope, appeared as faint, rounded, greenish disks, vaguely resembling the appearance of a planet like Uranus, which Herschel himself had discovered a few years earlier. He called them planetary nebulae, and the name, despite being based on nothing more than a passing visual resemblance, stuck permanently, even after astronomers fully understood decades later that these objects have absolutely nothing to do with planets at all. A planetary nebula actually forms at the very end of a sun-like star's life, once it has exhausted the hydrogen fuel in its core and expanded into a red giant. In its final stages, the outer layers of the star are gently expelled into space, forming a glowing shell of gas around the small, hot, exposed core left behind, a completely different process from the violent, explosive supernova death of a much more massive star. Despite the misleading name, planetary nebulae are genuinely some of the most visually striking objects in the night sky, often displaying intricate, symmetrical, and surprisingly delicate structures, rings, hourglasses, and butterfly-like shapes that still aren't fully explained by current models of exactly how a dying star sheds its outer layers. A name given by mistake more than 2 centuries ago that nobody has ever quite gotten around to correcting, a small, permanent monument to how easily an early guess can outlive the actual truth it was guessing at. Every planetary nebula has its own personality. 2, in particular, have become favorites. One shaped like a ring, one shaped like an eye. The ring that isn't actually a ring at all. Roughly 2,600 light-years away, in the constellation Lyra, sits one of the most famous planetary nebulae in the sky, the Ring Nebula, a glowing shell of gas around a small, hot, dying star, first discovered in 1779. For over 2 centuries, telescope images consistently showed it as a simple, softly glowing ring, a bright band of gas surrounding a darker central gap. It's a striking, deceptively simple shape, one of the most viewed objects by amateur astronomers, precisely because it's bright and clear enough to be easily found with a modest backyard telescope. But detailed observations by the Hubble Space Telescope, and later, far more detailed imaging from the James Webb Space Telescope in 2023, revealed that the Ring Nebula isn't really a flat ring at all. It's closer to a distorted barrel or football shape, and we simply happen to be viewing it almost directly down one of its open ends. The apparent ring is really more like looking straight through a hollow tube, seeing its brighter walls as a circle from our particular angle. Webb's imaging also revealed roughly 20,000 dense, small clumps of gas embedded within the nebula's structure, along with faint concentric arcs in the outer material. Evidence, some astronomers believe, of an unseen companion star whose gravity shaped the dying star's outflow into the layered pattern we now see. A shape everyone assumed they understood perfectly for over 200 years, simply because nobody had ever had a clear enough view to notice they were looking straight down its throat the entire time. The nebula that looks like it's watching you back. Roughly 650 light-years away, in the constellation Aquarius, the Helix Nebula has earned an evocative nickname, the Eye of God, for its striking resemblance in telescope images to a vast, glowing eye staring back out of the darkness. As one of the closest planetary nebulae to Earth, the Helix appears unusually large in the sky, which allows telescopes to resolve an extraordinary amount of fine structure within it, including thousands of small, comet-like knots of denser gas throughout the nebula, each trailing a faint tail pointing away from the central dying star, shaped by that star's outward stellar wind. Infrared observations have also revealed a surprisingly complex, disk-like structure of dust encircling the central white dwarf, along with evidence suggesting the system may include a very faint, previously undetected companion. Findings that continue to complicate the once simple picture of exactly how a planetary nebula's structure actually takes shape. Because of its proximity and clarity, the Helix has become one of the most extensively studied planetary nebulae in the sky, offering astronomers an unusually detailed real-world example of the process every sun-like star, including our own, will eventually go through. A vast, glowing eye, 650 light-years away, that isn't looking at anything at all, just the last, quiet light of a star, finishing the only ending a star like it is ever given. We've seen what these dying stars leave behind. Let's slow down and look at the actual moment a star like our own sun begins to die. The slow, gentle way a sun-like star actually dies. A star like our own sun spends the overwhelming majority of its life, roughly 10 billion years in the sun's case, quietly fusing hydrogen into helium in its core, in a long, stable phase astronomers call the main sequence. Once the hydrogen fuel in the core is finally exhausted, the core contracts and heats further, while the outer layers of the star expand dramatically and cool, transforming the star into a red giant, potentially large enough, in our own sun's case roughly 5 billion years from now, to expand out past the orbit of Mercury and possibly Venus. Eventually, the outer layers become loosely bound enough that they drift away entirely into space, pushed outward in slow, gentle pulses over thousands of years. Rather than being blasted away all at once, this expelled material is exactly what becomes a planetary nebula, glowing gently around the small, hot core left behind. Unlike the far more massive stars we'll look at shortly, A sun-like star's death involves no explosion at all, just a long, unhurried release, the star essentially breathing its outer layers out into space over a period that, cosmically speaking, still counts as remarkably gentle. 10 billion years of quiet, steady burning, ending not with violence, but with a slow exhale, the same soft ending waiting 5 billion years from now for the very sun currently keeping you warm. The small, stubborn ember left behind. Once a sun-like star has shed its outer layers into a planetary nebula, what remains at the center is an extraordinarily dense, small object called a white dwarf, roughly the size of Earth, yet containing a mass comparable to the Sun itself. A single teaspoon of white dwarf material would weigh several tons here on Earth, nowhere near as extreme as the neutron stars we discussed in an earlier episode, but still far denser than anything found naturally on Earth's own surface. This density comes from a strange quantum effect called electron degeneracy pressure, which holds the white dwarf's structure stable, preventing it from collapsing further under its own gravity. A white dwarf has no fuel left to burn and produces no new energy of its own. It simply radiates away the residual heat left over from its former life as a star's core, slowly cooling over an immense span of time. Current models suggest it would take longer than the current age of the entire universe for a white dwarf to fully cool into a cold, dark, inert object, sometimes called a black dwarf. This means that, as far as astronomers can tell, no black dwarf has ever actually formed anywhere in the universe yet. Every white dwarf that has ever existed is technically still cooling patiently, some of them for well over 10 billion years already, with unimaginably more time still ahead of them. A small, stubborn ember, left over from a star that's already finished living, still glowing faintly, and expected to keep glowing faintly for longer than the universe itself has existed so far. That's how a star like our Sun ends. A far more massive star ends very differently and far more violently. The death loud enough to outshine an entire galaxy. Stars significantly more massive than our Sun, roughly 8 times or more, meet a dramatically different end. Rather than gently shedding their outer layers, they die in a sudden, catastrophic explosion called a supernova. Once such a massive star exhausts its nuclear fuel, its core can no longer support itself against gravity and collapses in a fraction of a second. That sudden collapse triggers a colossal explosion, blasting the star's outer layers into space at tremendous speed and briefly producing more energy than the star released during its entire previous lifetime combined. For a short period, a single supernova can genuinely outshine every other star in its entire host galaxy. The material blasted outward from a supernova doesn't simply vanish. It enriches the surrounding interstellar medium with heavy elements forged both during the star's life and in the explosion itself, material that will eventually become part of future generations of stars, planets, and, in at least one documented case, the elements that make up living things. What's left behind depends on the original star's exact mass, either an extraordinarily dense neutron star, similar to the ones discussed in an earlier episode, or, for the most massive stars of all, a black hole forming from a collapse so complete that not even light can escape it. A death loud enough for one brief moment to outshine every other star for thousands of light years in every direction, and quiet enough afterwards to leave behind either a small, impossibly dense ember or nothing that light can ever climb back out of again. That's the theory of a supernova. One of them was actually recorded in careful detail nearly 1,000 years ago. The explosion Chinese astronomers wrote down in 1054. In July of the year 1054, Chinese court astronomers recorded the sudden appearance of an extraordinarily bright new star in the sky, in the constellation we now call Taurus, describing it as bright enough to be visible in daylight for roughly 3 weeks. Their careful, dated records, along with corroborating observations from Japanese and likely indigenous American astronomers around the same period, give modern astronomers an unusually precise historical anchor for something otherwise very difficult to date directly: the exact moment a specific supernova occurred, visible from Earth. We now know that new star was a supernova, marking the explosive death of a massive star roughly 6,500 light-years away, meaning the actual explosion happened 6,500 years before 1054, and its light simply took that long to finally reach Earth, arriving at a moment careful observers happened to be watching and, crucially, writing it down. The expanding wreckage from that explosion is still visible today and still expanding, a glowing, intricate cloud of gas we now call the Crab Nebula, one of the most thoroughly studied supernova remnants in the entire sky, precisely because we know with unusual historical precision exactly when its story began. A star exploded twice, in a sense, once silently, 6,500 years before anyone on Earth could know about it, and once again nearly 1,000 years ago, when careful hands finally wrote the date down. The heart still spinning inside the wreckage. At the very center of the Crab Nebula sits the collapsed core of the star that exploded in 1054, a neutron star spinning an astonishing 30 times every single second, sweeping a beam of radiation across space with each rotation, making it what astronomers call a pulsar. The Crab Pulsar was one of the first pulsars ever identified with a known dated origin, making it an unusually valuable laboratory for studying exactly how these objects behave shortly after formation, in astronomical terms. Shortly here still meaning nearly 1,000 years, but genuinely young compared to most other known pulsars. Despite being only about 12 miles across, the Crab Pulsar generates a powerful magnetic field and an intense wind of charged particles, which is what actually powers much of the surrounding nebula's continued glow. The pulsar isn't just a passive relic sitting at the center. It's actively energizing the wreckage around it, nearly 1,000 years after the original explosion. Astronomers have also detected the Crab Pulsar gradually slowing down over time, losing energy as it radiates it away, a slow, measurable spin down that offers a rare, direct way to study how these extreme objects age, tracked continuously since the pulsar itself was first identified in 1968. A city-sized heart, spinning 30 times a second in the wreckage of its own explosion, still quietly powering the very cloud of debris it created nearly 1,000 years after anyone first wrote its birth down. The Crab Nebula is one supernova remnant. There's an older, larger, quieter one worth visiting too. The delicate lace left by an ancient explosion. In the constellation Cygnus, roughly 2,400 light-years away, delicate, thread-like wisps of glowing gas stretch across a region of sky many times wider than the full moon, the Veil Nebula, remnant of a massive star that exploded somewhere between 10,000 and 20,000 years ago. Unlike the relatively compact, intensely bright Crab Nebula, the Veil has had far more time to expand and thin out, spreading its material across a vastly larger area of sky and taking on a delicate, lace-like structure that looks, in long exposure photographs, almost more like a wisp of smoke than the aftermath of a stellar explosion. This filamentary structure forms as the outward-moving shock wave from the original explosion collides with surrounding interstellar gas, compressing it into thin, glowing sheets that appear, from our vantage point, as delicate curved threads rather than a solid cloud, genuinely three-dimensional structures that simply look flat and lace-like from any single viewing angle. The Veil is large enough that different sections have earned their own individual names and catalogue numbers among astronomers and astrophotographers, despite all being fragments of one single, ancient, continuously expanding shockwave, a single event tens of thousands of years old, still slowly writing itself larger across an ever-widening patch of sky. Lace made of shock wave and gas, tens of thousands of years old, and still quietly, patiently expanding, proof that even a violent ending can settle, eventually, into something this delicate. We've spent a long time zoomed in on single nebulas. Let's pull back now, much further, to the galaxy holding all of them. The shape of the galaxy we actually live inside. Every nebula we visited tonight sits within our own galaxy, the Milky Way, a vast spinning collection of an estimated 100 to 400 billion stars, along with enormous quantities of gas, dust, and dark matter, spanning roughly 100,000 light-years across. Determining the Milky Way's actual overall shape has historically been a genuinely difficult problem, precisely because we're observing it from deep within one of its own spiral arms, a bit like trying to draw an accurate map of an entire forest while standing among the trees, unable to step back far enough to see the whole layout clearly. Based on decades of careful mapping, tracking the positions and motions of stars, gas clouds, and star-forming regions, astronomers currently understand the Milky Way to be a barred spiral galaxy, meaning it has a central elongated bar-shaped structure of stars with spiral arms winding outward from each end of that bar, similar in overall structure to a large share of spiral galaxies observed elsewhere in the universe. Our own solar system sits roughly halfway out from the center, within a relatively minor spiral arm called the Orion Arm, sometimes called the Orion Spur, meaning even our galaxy's own most iconic nebula from earlier tonight shares a rough cosmic neighborhood with the very sun and planets currently reading or listening to this sentence. An entire galaxy home to every nebula, every star, and every dying and newborn light we visited tonight, and we're still, even now, working out the exact shape of the very structure we've called home for our entire existence. The galaxies that don't bother with a spiral at all. Not every galaxy shares the Milky Way's elegant spiral structure. Astronomers broadly sort galaxies into several major categories, and two of the most common alternatives are elliptical and irregular galaxies, each looking and behaving quite differently from our own. Elliptical galaxies appear as smooth, rounded collections of stars, ranging from nearly spherical to distinctly elongated, with far less of the gas and dust needed for active star formation compared to spiral galaxies. As a result, elliptical galaxies tend to be composed mostly of older stars, with relatively few new ones currently forming within them. Some of the largest known galaxies in the universe are giant ellipticals, often found at the crowded centers of large galaxy clusters. Irregular galaxies, as the name suggests, lack any clear, organized structure at all. No defined spiral arms, no smooth elliptical shape, just a somewhat chaotic distribution of stars and gas. Many irregular galaxies are thought to have been reshaped by close gravitational interactions or collisions with neighboring galaxies, their original structure disrupted by the encounter. Two of the most famous irregular galaxies, the Large and Small Magellanic Clouds, are actually visible to the naked eye from the southern hemisphere, appearing as faint, cloud-like smudges, small satellite galaxies gravitationally bound to our own Milky Way, slowly being pulled apart and absorbed by it over an immense span of time. Not every galaxy needed a spiral to be worth studying. Some simply settled into a smooth, quiet sphere, and some never quite settled into any particular shape at all. Not every spiral is subtle, either. One nearby galaxy shows off its structure about as clearly as any galaxy ever has. The spiral's so perfect, it became a textbook example. Roughly 23 million light-years away, in the constellation Canes Venatici, the Whirlpool galaxy presents one of the clearest, most well-defined spiral structures of any galaxy known. Sweeping arms of stars and gas winding outward from a bright central core, visible in almost textbook clarity. Part of what makes its spiral structure so strikingly well-defined is a smaller companion galaxy, visible nearby, gravitationally interacting with a whirlpool's outer edge. Astronomers believe this ongoing interaction has actually helped trigger and enhance star formation along the spiral arms, compressing gas clouds and lighting up the arms with young, bright stars that make the overall structure even more visually distinct. First observed in 1773, the Whirlpool became one of the first galaxies in which astronomers could clearly identify a spiral structure at all, well over a century before the basic nature of galaxies themselves as vast, separate collections of stars, distinct from our own Milky Way, was properly understood. It remains a favorite target for both professional and amateur astrophotographers today, precisely because its structure is bright and clear enough to be genuinely appreciated even through relatively modest telescope equipment, unlike many fainter, more distant galaxies that require significantly more powerful instruments to resolve any real detail at all. a perfect spiral, 23 million light-years away, partly shaped into its best-known form by a smaller neighbor's gravity. Even galaxies, it seems, sometimes need a little outside help to become their most photogenic selves. The galaxy making stars faster than it probably should. Roughly 12 million light-years away, in the constellation Ursa Major, the Cigar galaxy is undergoing an extraordinarily intense burst of star formation, producing new stars at a rate roughly 10 times faster than our entire Milky Way, packed into a galaxy a fraction of the size. Astronomers classify this kind of object as a starburst galaxy, and the Cigar galaxy is one of the closest and most extensively studied examples in the sky. This intense star-forming activity was very likely triggered by a close gravitational encounter with its much larger neighbor, generating powerful gravitational disturbances that compressed the galaxy's gas clouds and dramatically accelerated star formation throughout much of its structure. All of this rapid star birth comes at a cost. The Cigar galaxy is also known for enormous outflows of superheated gas, visible in specialized imaging, streaming outward from its center for thousands of light years, driven by the combined stellar winds and supernova explosions of so many massive stars forming, living brief lives and dying in such rapid succession, all within a relatively compact space. Because starburst activity this intense generally can't be sustained indefinitely, the available gas supply eventually gets consumed or blown away entirely. Astronomers consider the Cigar galaxy to be in a genuinely temporary, dramatic phase of its much longer overall life, one that, cosmically speaking, won't last especially long before slowing back down. An entire galaxy burning through its own fuel roughly 10 times faster than ours in a brilliant temporary burst that it very likely won't and, in a sense, structurally can't keep up forever. Galaxies come in many shapes. Within them, stars themselves gather into their own smaller, tighter communities too. The ancient spherical cities made entirely of stars. Scattered around the outer regions of most galaxies, including our own Milky Way, are globular clusters, tightly packed, roughly spherical groupings that can each contain anywhere from tens of thousands to several million stars, all gravitationally bound together in a space just tens to a couple hundred light-years across. Globular clusters are among the oldest structures found in most galaxies, with stars in many of them estimated to be over 10 billion years old, meaning the stars in a typical globular cluster formed when the universe itself was still relatively young, not long after galaxies themselves first began taking shape. Near a globular cluster's densely packed core, stars can be so close together, sometimes less than a light-year apart, compared to roughly 4 light-years between our own sun and its nearest stellar neighbor, that a hypothetical night sky viewed from a planet near the cluster's center would show hundreds or even thousands of stars far brighter than anything visible from Earth. Astronomers still debate exactly how globular clusters originally formed and why their stars are almost all roughly the same, very old age, unlike more loosely bound open clusters, which we'll look at shortly, that often contain stars of noticeably varied ages a genuinely open question in an otherwise well-studied ancient corner of galactic astronomy. Ancient, tightly packed cities of stars, some of them older than most of the galaxies surrounding them, quietly orbiting the outskirts of galaxies, holding some of the oldest starlight most of us will ever actually get to see. The largest star city in our entire galaxy. Of the roughly 150 known globular clusters orbiting our own Milky Way, one stands out dramatically from the rest: Omega Centauri, visible to the naked eye from the southern hemisphere, containing an estimated 10 million stars, making it, by a wide margin, the largest and most massive globular cluster in our entire galaxy. Omega Centauri is so unusually massive, and its stars show such a surprisingly wide range of ages and chemical compositions compared to typical globular clusters that many astronomers now believe it isn't a true globular cluster at all. In the traditional sense, it may actually be the stripped, surviving core of a small dwarf galaxy that our own Milky Way gravitationally captured and largely dismantled over billions of years, leaving only its dense central core intact. Supporting this theory, some observations suggest the presence of a possible intermediate mass black hole near Omega Centauri's center, a genuinely rare kind of object, far smaller than the supermassive black holes found at galaxy centers, but far larger than a typical stellar black hole, exactly the kind of remnant that might be expected at the core of a small galaxy long since absorbed by a much larger one. If this theory holds up under continued study, Omega Centauri represents something genuinely rare and valuable to astronomers. A fossil record of an entire small galaxy, largely consumed by our own, still hanging on to just enough of its original identity to be recognized for what it very likely once was. 10 million stars orbiting together that may not be a star cluster at all, quite possibly the last surviving heart of an entire separate galaxy, absorbed so long ago that only its core remembers it was ever anything else. Globular clusters are ancient and tightly bound. A much younger, looser kind of cluster is probably already familiar to you, even if you've never used a telescope at all. The stars still wrapped in the cloud that made them. Visible to the naked eye in the constellation Taurus, the Pleiades, often called the Seven Sisters, is one of the closest and most recognizable open star clusters in the sky. A loose grouping of several hundred stars, roughly 444 light-years away, formed together from the same collapsing molecular cloud within the last 100 million years or so. Unlike the ancient, tightly bound globular clusters from a few chapters ago, open clusters like the Pleiades are relatively young, loosely held together by gravity, and will eventually drift apart entirely over the next few 100 million years as individual stars gradually pull away from one another and disperse into the wider galaxy. Long exposure photographs of the Pleiades reveal the faint, wispy blue reflection nebula we discussed earlier tonight, still draped delicately around its brightest stars, a visible reminder that this cluster, cosmically speaking, is still remarkably young, close enough in time to its own formation, or at least to a chance dusty encounter, that traces of the surrounding cloud remain clearly visible. The Pleiades have held cultural and mythological significance across an enormous range of human cultures throughout history. appearing in ancient Greek mythology, Aboriginal Australian tradition, Japanese folklore, and Maori culture, among many others, each tradition independently noticing and giving meaning to the very same small cluster of stars. A handful of stars, barely 100 million years old, still faintly wrapped in the cloud that made them, recognized and named and wondered about by nearly every culture that ever thought to look up. Star clusters are held together by gravity we can measure directly. Something else, far larger, holds entire galaxies together, and we still can't say exactly what it is. The invisible grip holding galaxies together. As covered in more depth in an earlier episode, galaxies rotate far too quickly for their visible mass, all their stars, gas, and dust combined to gravitationally hold them together on its own. Something with substantial gravitational pull, but that emits no detectable light, appears to make up the difference. We call this missing mass dark matter, and its presence shapes far more than just rotation speed. Dark matter appears to form vast, roughly spherical halos surrounding entire galaxies, extending well beyond the visible edge of their stars and gas, an invisible scaffold in a sense, within which the visible glowing structure of a galaxy sits. This invisible scaffolding likely played a crucial role in galaxy formation itself. Billions of years ago, dark matter's gravity is thought to have been essential in gathering the first clumps of ordinary matter together in the early universe, before galaxies as we recognize them today had even begun to take shape. Every nebula, every star cluster, every galaxy we've visited tonight sits embedded within one of these invisible halos. The visible, colorful universe we've spent this whole episode looking at is, by current estimates, only a small fraction of everything that's actually out there holding it all together. Behind every glowing nebula and every spinning galaxy tonight, something unseen has been quietly, patiently doing most of the actual holding, gravity's grip still working from something we've never once actually seen directly. We've talked about what we can't see. Let's talk now about the telescope that finally let us see further than ever before. The telescope built to see through dust itself. Launched in December 2021 and beginning science operations in mid-2022, the James Webb Space Telescope was designed from the ground up to observe the universe primarily in infrared light, a deliberate choice that unlocks views of the universe no previous telescope, including Hubble, could fully achieve. Infrared light passes through clouds of cosmic gas and dust far more easily than visible light does, which is precisely why Webb can peer directly into the hearts of dense, dusty nebulas, like the Pillars of Creation and the Carina Nebula from earlier tonight, revealing newborn stars completely hidden from visible light telescopes, still fully wrapped in the dust of their own formation. Webb's enormous primary mirror, assembled from 18 hexagonal gold-coated segments and spanning roughly 21 feet across, gives it significantly greater light-gathering power than Hubble's much smaller mirror, allowing it to detect fainter, more distant objects with considerably greater clarity and detail. To detect faint infrared signals without its own heat interfering, Webb operates roughly 1 million miles from Earth, shielded by a tennis court-sized sun shield that keeps its instruments cooled to nearly absolute zero. An extraordinarily precise piece of engineering unfolded entirely in space, with no possibility of a repair mission if any part of that unfolding sequence had gone wrong. A telescope built specifically to see through the very same dust that makes nebulas glow in the first place, finally letting us look past the smoke straight into the fire, actually building each new generation of stars. The deepest photograph ever taken of anything. In July 2022, one of the first full-color images released from the James Webb Space Telescope showed a patch of sky roughly the apparent size of a single grain of sand held at arm's length, and within that tiny patch, thousands of individual galaxies, most never observed before. Called Webb's first deep field, the image was created by pointing the telescope at one small, seemingly unremarkable region of sky and collecting light for over 12.5 hours, allowing extraordinarily faint, distant light to gradually accumulate into a clear, detailed image. Some of the light captured had been traveling toward us for over 13 billion years, making it among the oldest light ever directly observed. The image also captured a striking natural phenomenon called gravitational lensing, which we touched on in an earlier episode. The combined mass of a massive foreground galaxy cluster visibly bends and magnifies the light of much more distant background galaxies, warping some of them into faint, curved arcs of light, and allowing Webb to see galaxies that would otherwise be far too faint and distant to detect at all. This single small patch of sky, chosen essentially at random, contained thousands of galaxies, each one containing, by extension, potentially hundreds of billions of stars of its own. A small, unremarkable-looking speck of the sky turning out to hold almost more than the mind can comfortably hold at once. A single grain of sand's width of sky, and thousands of entire galaxies hiding inside it. A fair reminder of just how much of the universe was always there, quietly waiting for a good enough set of eyes to finally notice it. Webb's deep field wasn't the first of its kind. A much earlier telescope tried something similar first, and almost didn't get approved to even try. The risky experiment that started it all. In December 1995, the Hubble Space Telescope was pointed at a small, deliberately unremarkable patch of sky near the Big Dipper, chosen specifically because it appeared to be nearly empty. No bright stars, no known notable objects, seemingly the least interesting patch of sky astronomers could find. Over 10 consecutive days, Hubble collected light from that single patch across 342 separate exposures, a genuinely risky use of extremely limited and valuable telescope time, since there was no guarantee the experiment would reveal anything worthwhile at all, and other astronomers could have used that same observing time for more conventional, likely to succeed research instead. The resulting image, called the Hubble Deep Field, revealed roughly 3,000 previously unseen galaxies crowded into that single, supposedly empty patch of sky. Direct visual proof that galaxies extend in every direction, essentially as far as any telescope has ever been able to look, transforming astronomers' basic understanding of just how much of the universe remained completely undiscovered. The experiment was considered such a success that it was deliberately repeated on other patches of sky in the years that followed, eventually inspiring the far more powerful, more detailed deep-field images captured by Webb decades later, a direct, traceable line from one bold, uncertain decision in 1995 to some of the most important images astronomy has ever produced. A patch of sky chosen specifically for looking boring and empty and unremarkable, turning out to hold thousands of entire galaxies simply because nobody had ever actually bothered to look closely enough before. Let's come back down from the deepest images ever taken to one of the busiest, most active nurseries known anywhere near us. The most crowded nursery in our cosmic neighborhood, located within a small satellite galaxy of our own Milky Way called the Large Magellanic Cloud. Roughly 160,000 light-years away, the Tarantula Nebula is the most active and productive star-forming region known anywhere in our local group of galaxies. At its center sits a densely packed cluster containing some of the most massive and luminous stars ever directly identified, including several individual stars, each estimated at well over 100 times the mass of our own Sun. Genuinely rare, extreme objects sitting together in a comparatively small, crowded region of space. Despite its considerable distance, the Tarantula Nebula is bright enough that, if it were as close to Earth as the Orion Nebula from earlier tonight, astronomers estimate it would be bright enough to cast visible shadows on Earth at night, a genuinely striking comparison, given that it's roughly 130 times farther away than Orion, and remains one of the most studied nebulas in the sky. The region also hosted the closest and most thoroughly studied supernova of the modern telescope era, observed in 1987, providing astronomers an invaluable, closely monitored real-world example of exactly how a massive star's explosive death actually unfolds, observed in significantly more scientific detail than the 1054 explosion from earlier tonight ever could have been. A nursery so crowded and so bright that, at the right distance, it could cast a shadow, quietly holding some of the most massive, most extreme stars we've ever managed to directly study, tucked inside a small satellite galaxy most people have never once heard the name of. We've looked at finished stars and dying stars. Let's go back to the very raw material every single one of them starts as. The raw material every single star was once made of. Every star we've discussed tonight, newborn or ancient, gentle or explosive in its death, began as part of a molecular cloud, a particularly cold, dense region of interstellar gas where hydrogen exists primarily in molecular form, rather than as the more common individual atoms found throughout most of the rest of a galaxy. These clouds are extraordinarily cold, often just 10 to 20 degrees above absolute zero, and can range enormously in size, from small, relatively compact clouds to giant molecular clouds spanning hundreds of light years and containing enough raw material to eventually form hundreds of thousands of individual stars. Despite containing all the necessary raw material, a molecular cloud doesn't automatically collapse into stars on its own. It typically requires some kind of external trigger, such as a passing shockwave from a nearby supernova or gravitational compression from the cloud's own passage through a galaxy's spiral arm. to push some region of the cloud over the density threshold needed for gravity to finally take over. Every nebula we visited earlier tonight, Orion, the pillars of creation, the Carina Nebula, is, at its core, simply a molecular cloud that has already crossed that threshold, now actively giving birth to the next generation of stars, using material that in some cases has been patiently drifting through the galaxy for a very long time before finally being pulled together. The coldest, quietest material in the entire galaxy, waiting patiently, sometimes for an immense span of time, for exactly the right nudge to finally become something bright enough to be seen from thousands of light years away. The spinning disk, where a new solar system takes shape. As a newborn star continues forming within its natal cloud, leftover gas and dust that didn't fall directly into the star settles into a flattened, spinning structure around it, called a protoplanetary disk, the same basic process that, roughly 4.6 billion years ago, produced our own sun and, eventually, every planet in our solar system. Within this disk, tiny particles of dust gradually collide and stick together, slowly building up into larger clumps, then small rocky bodies, then eventually the much larger planetary building blocks called planetesimals, a patient, incremental process that, given enough time, can assemble everything from small asteroids to entire gas giant planets. The James Webb Space Telescope, along with specialized ground-based observatories like ALMA in Chile, has directly imaged numerous protoplanetary disks around nearby young stars, in some cases revealing distinct gaps and rings within the disk, likely evidence of planets already forming and actively clearing debris out of their own individual orbital paths, caught in the actual act of assembling a new planetary system. These observations have given astronomers an unprecedented, direct window into a process that, in our own solar system's case, finished forming long before there was anyone around to observe it happening. Watching, essentially in real time, other stars go through the same process that eventually produced our own sun, our own Earth, and everyone who has ever lived on it. A spinning disk of dust and leftover gas, patiently building rocks into planets, the very same quiet, incremental process that once built the ground currently under your own feet, or the bed currently under you right now. Most of what we've covered tonight involves heat, stellar birth, nuclear fusion, explosions. One nebula, remarkably, is defined by the exact opposite. The coldest place we've ever found in the entire universe. Roughly 5,000 light-years away, in the constellation Centaurus, the Boomerang Nebula holds a genuinely extreme title, the coldest known natural object in the entire universe, measured at approximately 1 degree above absolute zero, colder, remarkably, than the faint background temperature of space itself, left over from the Big Bang. This nebula formed around a dying, sun-like star rapidly shedding its outer layers, similar in basic principle to the planetary nebulae from earlier tonight, but happening here at an unusually fast extreme rate, with material expanding outward at speeds exceeding 100 miles per second. That extremely rapid expansion is precisely what makes the Boomerang Nebula so cold. As the gas rushes outward and expands this quickly, it cools dramatically. Through the same basic physical principle, that makes an aerosol can feel cold to the touch as its pressurized contents rapidly expand and escape, just happening here on an almost incomprehensibly larger scale. Discovered in 1980 and studied in greater detail through the following decades, the Boomerang Nebula remains a rare, extreme natural laboratory, an object colder than the vast majority of space itself, created not by an absence of heat, but by the sheer, violent speed of a dying star's final outward breath. Colder than the space surrounding it, made that way not by stillness, but by speed, proof that even an ending this gentle in principle can still, somehow, outdo the universe's own natural cold. One more kind of nebula before we close tonight. Not a birth, not a death, but a brief, violent, in-between moment. The jets, a newborn star, fires into space. As a young star is still actively forming, material doesn't simply fall inward smoothly. Some of it, caught in the star's strong magnetic field, gets launched back outward in narrow, high-speed jets. And where those jets slam into surrounding gas, they create small, glowing patches called Herbig-Haro objects. Named after the two astronomers George Herbig and Guillermo Haro, who independently studied them in the 1940s and 50s, these objects appear as small, bright, often elongated knots or streaks of glowing gas, sometimes stretching for a light year or more away from the young star producing them. Because the jets themselves are narrow and can shift directions slightly over time as the young star wobbles, Herbig-Haro objects sometimes appear in pairs launched in opposite directions from the same source and can occasionally be observed actually changing position over a period of just a few years, a genuinely rare case in astronomy where a change is fast enough to be directly measured within a single human lifetime rather than over thousands or millions of years. Studying these jets gives astronomers valuable insight into the earliest, most turbulent stages of a star's formation, a brief, energetic phase, typically lasting only a few tens of thousands of years, that happens before the young star fully settles into the long, calm, stable adulthood that will define most of the rest of its life. A newborn star's brief, restless tantrum, firing narrow jets of glowing gas out into the dark. One of the only sights in this entire episode fast enough to actually watch change just a little within a single human life. The same ending waiting, very patiently, for our own sun. We open tonight by asking what a nebula actually is. We'll close by coming back one last time to the star currently keeping you warm, because everything we've covered tonight is, eventually, also its story. In roughly 5 billion years, our own sun will exhaust the hydrogen fuel in its core, swell into a red giant, and, following the same gentle process from earlier tonight, slowly breathe its outer layers out into space, becoming, for a brief cosmic moment, its own small, glowing planetary nebula with a white dwarf ember left quietly behind at its center. That future nebula won't be dramatic or violent. Our sun isn't massive enough to end in the kind of supernova we looked at earlier tonight. It will simply, gently become one more soft, glowing shell among the countless others scattered throughout the galaxy. its material eventually drifting back out into the same kind of cold molecular clouds that build the next generation of stars. In that sense, nothing we looked at tonight was ever really separate from anything else. The dust in an ancient nebula may well have come from a star very much like our own sun, dying gently billions of years before our own solar system even began to form, and our sun's own ending, 5 billion years from now, will quietly return the favor. Birth and ending, borrowed and returned, over and over, for longer than any of us will ever be able to watch. The whole slow, patient, beautiful cycle we spent tonight drifting through, and the very same one waiting gently for the star warming you right now. That's where we'll leave it tonight. A cloud that isn't really a cloud. A nursery visible to your own eyes. A star built from nothing but patient gravity. 3 towers, 4 light years tall. The same light building and unbuilding them at once. Cliffs made of gas and starlight. A glow that comes from the gas itself. A glow only ever borrowed. A cloud dark enough to hide the stars behind it. A shape that means nothing and instantly means a horse. A name given by mistake 2 centuries ago. A ring that isn't really a ring. An eye watching nothing at all. The slow, gentle way a star like ours actually dies. A small ember, outlasting the age of the universe so far. A death loud enough to outshine a galaxy. An explosion written down by careful hands nearly 1,000 years ago. A heart still spinning in the wreckage. Delicate lace, tens of thousands of years old. The actual shape of the galaxy we call home. Galaxies that never bothered with a spiral so clear it became a textbook example. A galaxy burning through its fuel too fast to last. Ancient cities made entirely of stars. The largest star city in our galaxy, possibly not a star cluster at all. A handful of stars still wrapped in the cloud that made them. An invisible grip we've never actually seen. A telescope built to see through dust itself. Thousands of galaxies hiding in a single grain of sand. A risky experiment that started it all. The most crowded nursery near us. The coldest material in the galaxy, patiently waiting. A spinning disk, quietly building the ground under your own feet. The coldest place in the whole universe. A newborn star's brief, restless tantrum. And the same soft, gentle ending, patiently waiting 5 billion years from now for the very star keeping you warm tonight. None of it needs solving tonight. It never did. If your eyes are already closed, that's exactly where they should be. And if they're still open, just a little, there's another quiet corner of space waiting right after this one, whenever you're ready. No rush, no sound, just drifting gently into whatever comes next.